so you want to remember that if you're taking any type of certification exam, because those are tricky questions. I know when I get them, I have to sit and look at them and actually think about what they're asking me, you know, because you can make a mistake easy on those. So it causes more than 2,000 admissions to a burn center. I know this is not new news for a lot of folks, but what's the significance of being sent to a burn center? What does that mean? Third degree burns, right? Over how much percentage of your body?
40%.
40 or 50%, yeah. Over 50% of the body has received greater than a second degree burn. So when you get sent to a burn center, this isn't, you know, in at 10 in the morning and out at 3 in the afternoon. This is a commitment. And you know, and I don't know why it is, but it seems like every time I read about somebody that passed in a burn center, it seems to be that 10 days is this magic number. And I don't know why that is, but I always hear that the person lived 10 days and died. And of course, infection is one of the major challenges that people face when they enter into a burn center, because the body is so warm and not able to actually protect itself, so infection can set in. Sometimes people are in induced comas. It generally is going to mean skin grafting, and if you're lucky, that's all it is, without amputation, a lot of the other things that go along with it. It's not a very fun place to be. So obviously we know we have the arc flash can reach great distances. If you remember back in 2009, those of you that have been in the document for a while, there were significant changes made in the arc flash, the default arc flash boundaries in the 2009. The 4-foot arc flash boundary, what we called KA cycles at the time, which was a result of 50,000 amps of fault current, 6 cycles of clearing time, 6 times 50 was 300. Anything that gave you 300, what we called KA cycles, in the default boundary, you could use a 4-foot arc flash boundary. When West Tech, who makes arc-rated apparel, showed up at the 2009 70E meeting with their videos of blowing up equipment and enclosures, they realized that those arc flash boundaries weren't working. And they actually dropped it from 300 KA cycles to 100 KA cycles for the 4-foot arc flash boundary. So we realized that it can go significant distances. And then OSHA estimated that an average of at least 8 burn injuries from arcs occur each year involve employees under their rules. Again, to 12 non-fatal and 2 fatalities. And then you can see a large percentage were third-degree burns. So this is the one that I said we'll just kind of go through it. I'm just going to put this up here, and then I'll flip through some of the other slides, stopping here and there. We can always talk more about it if somebody feels we need to, but obviously when I think of arc flash, I think of the what is the available fault current that's there, what's how is it going to arc, and how long is it going to arc for. The time is the real key piece of this. Of course, all of the components factor into it, but the longer that the arc continues, the higher the burn energy is going to be, the more heat that's going to be created in that arcing event. So we'll talk more about this as we go through. So obviously voltage is a pressure. And interesting that when you work in some, and I know there's some folks here that probably work in some medium voltages, higher voltage applications. In some of the companies that I work at, where they have a lot of 2400 volt and 4160 and 12 or 13,000 or 15 kV type systems, they tend to treat 480 like it doesn't mean anything. And it's actually more hazardous than some of those higher voltages from a burn standpoint. It has a tendency to continue to burn versus to blow itself clear because of the lesser amount of the pressure not being as high as it would be in a higher voltage. So obviously we abbreviate it as V or E. And of course the current flow is the flow of electrons past some point in the circuit. So again, like I said, I'm going to just go through these because I think we got a lot of other things to talk about, and if somebody has a question or wants further explanation, please see me at the end of the day or at lunch or whatever, and I'll be happy to. So impedance can be a friend sometimes, and it may not be a friend sometimes. If it's going to reduce the amount of actual current that's going to flow, unless I'm using it as a safety measure to do that, it may lengthen the time that it takes for the overcurrent device to clear, which is ultimately going to result in a larger burn energy. And we're going to talk a lot more about that as we go through. So obviously, some of these I do like. So obviously, I got to have a difference in potential to create a hazard. You know, whether it's an arc flash hazard or whether it's a shock hazard, I've got to have a difference in potential to get to either one of these places. So I've got to have two sides of the circuit, or a phase to ground, or I've got to have some difference in potential to make it happen. So a circuit requires a difference of potential to operate, and it completes a conductive path. The load is actually the impedance, which determines the amount of current that flows in the circuit. So for example, when I look, and I don't know what we had with this one. So when I look at this, obviously I have to have a source, I have to have a difference in potential, and I have to have a load to make current flow. When we get a short circuit, we shorten up the circuit, and it takes the load out of the picture. We'll look at a couple other slides, so I'm not going to get too much into that at the moment, but obviously these are the essential elements of a circuit. The interesting point is, on a short circuit, the current flow stays in the insulated pathway. It doesn't energize the equipment, at least initially anyway. It doesn't energize the outer part of the equipment, whereas on a ground fault, I now have current flowing on the outside of the equipment, and my equipment grounding circuit or pathway, fault return path, becomes an extremely important part of the circuit. Because it's not just about grounding the equipment, it's about getting the fault current back to the source to open up the overcurrent device. If the overcurrent device doesn't open, then all bets are off. That's what happened to that worker on top of the lift. That 400 amp feeder faulted and the overcurrent device never opened. In that case, it was a system bonding jumper. This component right here was compromised in that installation, and so there was no way for the current to get from this point, from the enclosure, onto the grounded conductor and back to the source. And that's what delayed actually the device never opened. It actually burned a hole in the metal enough so that the arc kept far enough apart that it couldn't sustain itself, and it stopped arcing. So again, the current increases as the voltage increases. When I first read that, I was like, well, wait a minute, any motor circuit or anything I ever worked on, if the voltage was higher, the amperage was always less in the circuit. But what they meant here was, once I established the operating current, as the voltage increases, the current increases with that circuit, and decreases as the impedance increases. So again, you can see the normal pathway, the normal flow of the circuit, with the impedance actually being the load. So on this lighting circuit in this room right now, or lighting circuits probably, the actual current flow is determined by the load, right? It's determined by the ballast or the drivers in the luminaires or incandescent lamps, whatever they are. It is governing the actual amount of current flow normally in the circuit. So that's the normal circuit operation. So the overcurrent device obviously protects the circuits and the equipment. And then, of course, the NEC does not necessarily look at arc flash from an overcurrent device standpoint. In the last couple cycles, we have put language in, and you'll see it later on, when we have systems that are over 1,000 amps. You're required, like with a circuit breaker, for example, you're required to employ some type of arc flash mitigation. We'll talk about them later on in Article 240. So they do actually, so the NEC is starting to consider arc flash, but it's at a pretty high level at this point. It's not going to be an 800 amp panel. It's going to be a 1200 or a 15 or a 2000 amp panel board or switchboard or motor control center. You're going to have to employ some type of arc flash mitigation if it is a circuit breaker. In 2020, that will include fuse installations as well. So you'll see those. So 240-87, yeah, it was at 1,000 volts or less. It was 1,200 amps, I'm sorry. I couldn't remember what the threshold was. So 1,200 amps or higher, provided with the means of arc energy reduction. We'll talk about some of that. And here's the new language that is actually in the 2017 NEC, which becomes effective in January of 2020, unless they make some type of change in the next edition. of the document. So it's going to require some type of energy maintenance switching or some type of arc flash mitigation. So here's a couple of older videos. I think I have to see that. At least I'm assuming they are. And what it's trying to do, what these are trying to show is that obviously and you're going to see changes in the 70E. Actually, they tried to make some consistency out of the use of the terms of available fault current and short circuit current. So we give equipment short circuit current ratings, and we look at what the available fault current is where the circuits are, where we're actually doing the work or where the equipment is. So I do some training for Toyota manufacturing in the United States. I haven't been to Japan for them yet, but anyway, a friend of mine that I work with there calls it a coming out party. When we install equipment that is rated less from a short circuit current standpoint, when the available fault current is greater than the short circuit current rating of the equipment, as engineers, you all well know that the equipment can come apart. It won't sustain under a fault condition, it'll come apart. He calls that a coming out party, where all the pieces and parts come out the grate tree. It's not what we're trying to do. So you'll see that in these applications. There's 3 of these, and you'll see that they're showing an improper. They're not the greatest from a clarity standpoint. That's why I say they're older. But you can see that they intentionally create a short circuit between the 2 phases. And the intent is to show that if this is designed properly and it's installed properly within its ratings, it shouldn't come apart when it clears the fault. And that's the intent of it. Much love, slow motion. So obviously you can see there's some pretty...
This is a serious misapplication.
You can see there's some pretty extensive damage to the equipment. You gotta love it. Now this one you gotta be paying attention on this one, because this one's actually installed properly. That's it.
Notice that the fault has been safely cleared without any damage.
And then finally, this one here that really comes apart. And when we get into the definitions, what's that?
Yes, that's what we do.
That's what you do, right? So this is not new news to you guys, is it? You all.
Again, this is a serious misapplication.
Well, I'm sorry, what was that?
So we actually burn batteries.
I know, you told me, you guys do batteries. That's gotta be interesting. Okay. So anyway, obviously the intent is to install equipment within its operating range. So when we get into Article 100, you'll see that the 70E committee took a step forward this time in defining available fault current and short circuit current, and they actually put a figure in this time to kind of identify where they really are. The available, what we're concerned with is what is the fault current that's actually available at the point where we're working. So obviously overcurrent is a defined term in the NEC. It consists of it covers overloads, short circuits, and ground faults. So when 70E or when the NEC uses the term overcurrent protection or overcurrent, it includes overload, short circuit, and ground fault.